Okay, so today we'll be talking about higher order non-homogeneous ODEs with constant coefficient. This is in section 4.6. And all the problems today we'll be using the method of undetermined coefficients that we used back with first order and second order differential equations. So the concepts will not be new. It's just we'll be applying them to higher order differential equations. So let's just take a look at an example. So here we have a fourth order differential equation, and it's non-homogeneous because we have a function 24 on the right hand side instead of 0. So of course the first step in solving a non-homogeneous differential equation is to solve the corresponding homogeneous differential equation. And to do that we get the characteristic equation. Now this one's fairly simple because we have the r squared term and an r squared term, so we can just factor out r squared. When we do that, we just get r squared times r squared minus 16. And that's also an easy quadratic to factor. It's a difference of squares. So we end up with r squared times r plus 1 times r squared times r plus 4 times r minus 4. So what are our roots? Well, we have r squared equals 0. That gives us the repeated root of 0. r plus 4 equal to 0 gives us the factor r equals negative 4. And r minus 4 gives us the factor, the root r equals 4. So for the root 0, one solution is e to the 0 times t, which is 1, but it's repeated, right? So the second solution that corresponds to the root of 0 is t. We multiply 1 by t. For the root negative 4, our solution is e to the minus 4t. And for the root 4, we get e to the 4t. So remember, we're solving a fourth order differential equation. We need 4 solutions. We have them here. So our homogeneous solution is just the linear combination of those 4. Okay, so what's our next step? We need to find the particular solution. So just think back to how we did this with second order equations. Our function on the right hand side is 24. We call that f of t is 24. Now that's just a constant. So in our corresponding set of solutions, we just put 1 in our set. Now we have to ask the question, is 1 in our homogeneous solution? Yes, it is. There it was right there. It is a solution to the homogeneous equation. We multiply by t. So we get t. Is t in our homogeneous solution? The answer is yes. There it is. Multiply by t again, we get t squared. Is t squared in our homogeneous solution? No, it's not there. So we take our particular solution to have the form a constant a times t squared, the function in our set. So let's figure out, we need to find out what a is by substituting into our differential equation. So here we are substituting. We need to know our derivatives. So here's our particular solution. We need the fourth derivative to substitute into our differential equation. So if we have at squared, its derivative is 2at. Now the 2a is a constant, so the derivative of 2at is 2a. Now this is a constant. What's the derivative of a constant? It's 0. So the third derivative is 0, as is the fourth derivative. So now we're just substituting back into the original non-homogeneous differential equation to figure out what a is. So our fourth derivative is 0. Our second derivative is 2a, and that should equal 24. So negative 16 times 2a gives us negative 32a equal to 24. When we divide both sides by negative 32, we can simplify to get minus 3/4. So our particular solution is at squared, where a is minus 3/4. So of course in our general solution, our last step is just to add the homogeneous in our particular solutions, and that's what we get. So that's the solution to the non-homogeneous differential equation. Well, let's take a look at another one. So again, we have the same left-hand side of the differential equation. The function on the right-hand side is 24e to the 2t. So the first step is the same as before. We're just solving the corresponding homogeneous differential equation, and we've done that. So we'll just write it down. Now to find our particular solution, we're looking at the function on the right-hand side, 24e to the 2t. Now the important part about that is the e to the 2t, that exponential function. Our fundamental set of solutions here is e to the 2t. Now, is e to the 2t in our homogeneous solution? The answer is no. So we assume our particular solution is a e to the 2t. We're looking for a solution so that when we plug it in to the left-hand side of the differential equation, we'll get an e to the 2t to come out. So that's a good candidate. Now, what's the derivative? We take a times e to the 2t. The derivative of e to the 2t is e to the 2t times the derivative of 2t. So we just get 2a e to the 2t. The derivative of that is the same thing. Take the derivative of e to the 2t, which is 2e to the 2t, and multiply it by 2a to get 4a e to the 2t. We need the fourth derivative, so we need our third derivative. As we differentiate again, we'll end up multiplying again by the 2, so we get 8a, and then the same way, the fourth derivative, 16a e to the 2t. So this time when we substitute into our differential equation, our fourth derivative is 16a e to the 2t minus 16 times the second derivative, which was 4a e to the 2t. So that's 16a, and then we get minus 64a. 16a minus 64a gives us minus 48a. And so notice this left-hand side has an e to the 2t term, as does the right-hand side. So we compare the coefficients. Minus 48a and 24. So minus 48a is 24. Divide both sides by negative 48 and simplify. A is minus 1/2. So our particular solution is a e to the 2t, but a is minus 1/2. So we have minus 1/2 e to the 2t, and we would just add the homogeneous solution that we had here and our particular solution to form our general solution.